we've gotten to this point here where we say the terms of the alternating series are decreasing. We're going to add something, but we're going to subtract something that's less than that. After we subtract that, we're going to add something that's less than that, at least the absolute value of that. Therefore, okay, we approximate the series, the nth partial sum, the maximum error, or something called the bounded error, is the absolute value of the n plus 1 term, or the next term. We go to n equals 7. Guess what? The 8th term will be the most we're going to be off. This is called the alternating Taylor series error bound. For a converging alternating Taylor series with decreasing terms, the nth Taylor polynomial is bounded by the next omitted term. Okay. And we use the word next omitted because we know that sometimes the next term might be 0. So if the next term is 0, we're not going to say we have 0 error. We're going to have to go to the next term that's not 0, the next non-0 term. Okay? So let's take a look at a quick little easy example. We've got this series, and we're doing the 5th partial sum for this one. And then using that, we'll determine the maximum error, or the upper bound of the error bound. And then we'll also consider on what interval does S must lie. Okay? So first of all, let's find our 5th partial sum of this series. So S sub 5 would be our first term when n equals 1. This would be a negative 1/2. Our next one, we'll change this to a positive 1. The denominator will be 4. Next one will be back to negative 1. And then we're taking 2 to the 3rd power. And we'll keep going from positive 1 to negative 1. And then our denominator is going to go up to 16, and then subtract 1/32. Those of you who know how to use your fractions would get a negative 11/32 on this. Okay. That is the 5th partial sum of this. We know that there's going to be an error on this. We know this isn't going to equal that actual function because we only went out to 5. This, again, is our 5th term. This one is the 4th term. This one is the 3rd term that we're adding together here. Okay? We only stopped at 5. Okay? Now, since this is an alternating series, negative 1 to the n, and we know that the next term is always less than the previous term, we know that this is going to converge by our alternating series test. And here's the key. We're going to use this alternating series error to calculate our bounded error. It's just going to be our next term. So the error of the 5th partial sum of this one is simply going to be the absolute value of the 6th term. What's our 6th term? Well, it's going to be negative 1 to the 6th power, a positive 1, and 2 to the 6th power, or 64. The absolute value of that is 1/64. This answer here, negative 11/32, cannot be off more than 1/64. It might be 1/64 too high, or it might be 1/64 too low. Okay? Which tells us what to do here for the last part of this. What interval must S lie? The actual value of S will be the partial sum plus or minus the error of this one. In other words, we'll take 11/32 and add 1/64 to it and subtract 1/64 from it, and that's going to tell us what the actual value absolutely must be between. It will not be farther than that away. Can't be. Let's just do one more example just to make sure we understand what this is doing here. Okay? Again, looking at this one, we're going to first start off by calculating the fifth partial sum. The fifth partial sum n equals 1. Oh, this first one's going to be a positive, and of course 1 factorial is just 1. And then we're going to alternate positive, negative. The numerator we're just going to know is going to be positive, negative. Let's just look at the denominator. This, of course, will be 2 factorial, which, of course, is 2. Next, we're going to add 3 factorial, will be 3 times 2, which is 6. Then subtract 4 factorial. 4 factorial will be 6 times 4, which is 24. And then our fifth one will be a positive one, and that'll be 5 factorial, which is the 24 times 5, or 120. This works out to be 76 120ths, which does reduce to 19/30ths, little smaller numbers for us. Okay. Now, how close is that to the actual value? Since this is a alternating series, decreasing alternating series, we know that our error for this fifth partial sum will be whatever the sixth term is. This one here is the fifth term. So the next one's going to be a negative, and it'll be 6 factorial. 6 factorial will be 120 times 6, or 720. Absolute value of that is 1 over 100, or 720. Which means that the actual value of this one must be between this fifth partial sum, oops, that was a positive, 19/30ths, plus or minus this 720, 1/720th. Okay. Let's consider another one. This time, we're just using the fourth partial sum. So let's start out with our first one. First one is going to end up being a positive. 2 times 1 gives us 2 in the denominator. Next one's going to be a negative. 2 times 2 gives us 4. Positive. 3 times 2 gives us 6. And then a negative 1/8. Okay. I used a calculator this time, and this gave me 0.2916 as a decimal. Okay. So if I use that fourth partial sum, what error would I expect to have? What's my maximum error? The upper bound of the error, whatever wording they use. That error, because we're using the alternating series bound, will just be the absolute value of the fifth term. Our fifth term will be 1, and then 5 times 2, 1/10, or 0.1. Find the smallest n for which S sub n will give us a maximum error of 0.005. Okay? So, what's happening this time? Well, this is saying, hey, we did the fourth series partial sum, and we were this far away with an error of 0.1, but the engineer said not good enough. we're only accepting an error of 0.005. You got to get closer. Well, how many terms will that be? Okay, in other words, what is n going to be? Well, remember, our error of the nth partial sum will always be the n plus 1 term. Well, we know how to get the n plus 1 term because we've got the formula up here, right? It will be the absolute value of -1, n plus 1 would be n plus 2 here. And in reality, that's not going to matter to us at all because we know we're doing the absolute value anyway. But I'm just writing it down just to make sure you see that. And then, of course, this will be a 2 times the n plus 1. This has to be less than or equal to 0.005. Okay. So let's just solve this inequality. Remember, the numerator, no big deal. It's just going to be a positive 1. The denominator, when we distribute this, will be a 2n plus 2. That has to be less than, what is this? 10, 100, 5 thousandths. We can do some middle school cross multiplying here to get our cross products. Of course, 1 times 1,000 gives us 1,000 is less than 10n plus 10. Subtract the 10. Divide by 10. Then flip this around so it goes the way we want. And guess what? If we want to meet what the engineer said and get the error no more than 0.005, we're going to have to use at least the 99th partial sum on this one. So rev up that computer. You're going to have to go out 99 terms on this one, okay, in order to be that close. All right? So, on this idea of accuracy, this one said, hey, we want a maximum error of this. Sometimes they're going to word it a little bit differently. They'll say, we want an accuracy to 2 decimals. You probably had some problems like that before. Hey, give your answer to 2 decimals. Well, if it's the accuracy, that means we need at least 2 zeros in the error bound. And remember, it's going to go this way and that way. We're going to do a plus or minus on this. So in reality, we want this, if they use this phrasing, then you're going to do an error of 0.005. Those are the 2 zeros, the 2 decimal places. Okay? So in other words, the last problem that we did, instead of saying with a maximum error of this, they could have said with an accuracy of 2 decimal places, and we would do the exact same thing. Okay? So again, if I take this exact same problem on the homework and cut this out and paste this in, all the answers, everything's going to be the exact same. Okay? If they say 3 decimals, then of course, goes by logic that we need 3 zeros, and this would be 0.0005. So let's do another one here. It says find a 3rd degree Taylor polynomial for the sine of x. Well, that's one that we have memorized, right? We know what that Taylor polynomial is going to look like. We know that the 3rd degree, I'll put a 3 here. Remember, sine is our odd function, so it'll be the x to the 1st power, and then minus our x cubed over 3 factorial. No, I'm not going to put 3 terms on here. It said to the 3rd degree, not 3 terms. Okay? Now, it says use this to estimate the f of 0.2. You guys have done this. We did some homework on this one. Okay? So, f of 0.2 will be approximately the partial sum of 0.2, which would be 0.2 minus 0.2 cubed divided by 3 factorial, which is 6. And that's going to give us an amount of 0.198, and then 6 repeating forever and ever. Okay? Hey, how close is that? What's the error in this? That's part C. It says, hey, what is the maximum error? Or again, it could say the error bound. I'm putting both of these on here because the homework may only say what is the error bound. Or the homework might just say what is the maximum error. Same thing. Error bound, maximum error, same thing. Don't get messed up with those. Okay? So, hey, wait a second. We know that this series is an alternating series. Each term is less than the previous one. So, in order for us to find our error for this one, using the alternating series error, it's just going to be the next admitted term. Well, think about this. Our next term here is actually a 0. X to the 4th power is 0. Our next admitted term is actually what we might consider that 5th term in here. Okay? Because that's just the way these terms are set up, right? So, what's that going to be equal to? It's going to be the absolute value of x, or 0.02, to the 5th power divided by 5 factorial. Okay? So, you've got to know your series. Okay? The next admitted term, even though this is the 3rd term in there, okay, the 3rd degree term, the next one wouldn't be to the 4th power divided by 4 factorial. I guarantee you that that's going to be one of the answers on the multiple choice. But that term doesn't exist. Okay? So make sure that you remember this is the next omitted term. They like to ask questions like that. So make sure we don't get messed up on that. Those of you who were able to put that in your calculator would see that this is 0.00000, I think I got that right, 266. That's not too shabby. And we would say that this is an accuracy to 1, 2, 3, 4, 5. What's the accuracy? It's accurate to 5 decimals. Okay. Just kind of the reverse of what we set up above. Just working backwards to that. All right, so that's method number 1, nice and easy. Love that. Okay, but of course, not all series are alternating series. Not all alternating series are decreasing alternating series. So everything else, we're going to do this one named after a guy named Lagrange, or Lagrange, if you're better at French than me, but it goes like this. It says the Lagrange remainder formula is this mess right here. Okay? That actual error or remainder, same thing. That remainder or error is always going to be less than a capital M over n plus 1 quantity factorial times the absolute value of b minus n to the n plus 1 power. Okay, so this is equal to the exact difference between the exact value and our polynomial. The remainder is extremely difficult to find. Therefore, an estimate of the maximum error is found using this formula. Okay, so that's why you'll see that even with this one, it's saying, you know what, it's going to be less than this. So we're still estimating here. We're saying, hey, things are so hard for us to calculate with these series. We're just going to accept that there is a little bit of range here in our error. So we're going to make sure it doesn't exclude or doesn't go over this amount. So how is this calculated? Okay, so first of all, if a polynomial of n degree is used to represent the function, the remainder formula is always based upon, look at this, the n plus 1. So if we are using the seventh partial sum, our seventh remainder will use the eighth derivative in here. Okay, so A is always going to be what we're going to be centered around. That's that little number right there, A. Okay. In other words, when we have, hey, write a polynomial of x near A, if A is 0, then that's going to be 0. If A is 3, then that's going to be 3. Okay. B is our input value. When it says something like this, use the polynomial to approximate f of b. Last one, our b value would have been 0.0 or 0.2. Okay, that's our b value. Okay. M is the maximum absolute value of the derivative. Okay, this should look like our Taylor polynomial, doesn't it? N plus 1 factorial, n plus 1, basically x minus a. This m then represents the n plus 1 derivative. Okay? So again, this m is going to be our n plus 1 derivative of whatever this thing is. I'll just use z for some other number. We know that z, whatever that is going to be between those two numbers a and b that we have up there. Okay? All right. So the value usually is going to be given to us in the question. Let me repeat that, because this is key. The value is usually given. They're going to say m equals 4 or 4.1 or something like that. They're going to usually give you to that. Uh-oh, he did say usually. That means sometimes it will not. Okay? If it doesn't, we may have to calculate it, or we're going to straight up just use an estimate. So memorize these. If the function is e to the x, we're going to estimate m as 3. Okay? We know that e to the first power is 2.718. All right, we'll round it up and use 3. Just remember it that way. Okay? If it's e to the square root of x, we're going to use the square root of 3, which is approximately 1.8. If we have a sine or a cosine, sine and cosine, maximum values are 1, so our m will be 1. Okay? So again, these are 3 that are accepted to use as an estimate if we're using those functions. Every other function, we're going to have to use something else. We're going to have to use that derivative. Okay? So let's take a look at this. It says let f be a function with 5 derivatives on the interval from 2 to 3. They give us the fifth derivative. The fifth derivative is always less than 0.02 for all x's in this interval. If the fourth polynomial for f at x equals 2 is an estimate of f of 3, how accurate is this estimation? Okay, so real quickly, let's look at what we have here. Fourth degree polynomial means that n equals 4. fourth degree polynomial means that our next term, our n plus 1, is 5. Interpret this next one. It says at x equals 2. That's implying that our a value equals 2. Then it says use this polynomial to estimate f of 3, which means our b value is 3 in our formula. How accurate is this? Okay. So, remember what this looks like. The Lagrange, using the fourth degree polynomial, at the b value of 3 will be less than or equal to our m value. And remember, if m isn't given to us, if it isn't one that we know, we're going to set m equal to the n plus 1, or fifth derivative, of this function at 3. Mr. Dunn, they don't give us a derivative or a function here that I can take 5 derivatives of. You're right, there aren't. Okay? If they did give us the function, we might be able to use that. But wait a second here. What did they say? It is not garbage. This is called derivatives. Derivatives are not garbage. Kids these days. Okay? So, fifth derivative here. Well, the fifth derivative is always going to be less than 0.2. So really what they're telling us is that this m is always going to be less than or equal to 0.2. So that's what we're going to substitute in here. For the m value, 0.2. Remember, the denominator is based upon n plus 1 factorial. We know our n plus 1 is 5. And then that gets multiplied by the absolute value of b minus a. B is 3, a is 2. Oh, that was nice of them. 3 minus 2, of course, is 1. And then also remember, this is all raised to the 5th power. Okay? So, before I finish the calculation here, do not stress. Remember, a Taylor series. A Taylor series, every term in a Taylor series is the nth derivative at a divided by n factorial times x minus a to the nth power. Right? Do I need to keep memorizing this? No, I already have that memorized. Okay, look what Lagrange did. He stole Taylor's formula, right? Boy couldn't even create his own thing. Stole it from Taylor. Didn't even say, oh, this is the Taylor error bound. He stole the name. But it's still a Taylor polynomial here. Okay, this m is the n plus 1 derivative. Our denominator is n plus 1, and we're taking x minus a to the n plus 1 power. Okay? Can't be that bad? So think about it. With our alternating series, all we did was use the next omitted term. If we change to Lagrange, what are we doing? We're just looking at that next Taylor polynomial. So really looking at the next one anyway. Okay, kind of the same thing we did before. All right? So, nothing new that we have to memorize in reality. And of course, if we did work this out, this would be 1 times 0.02, 5 factorial, what is that, 720? I think that's what it is. which would simplify to, no, what's that? 4 times, now I'm getting a brain fart. Yep, that's, yeah. 1/600ths, what it should be. Okay. Now, let's take a look at our next example. It says, write down the second degree Taylor polynomial for e to the x. Okay. That's pretty easy. We've got this memorized. Second degree. Remember, the first term is 1, the second term is x. We're not stopping at 2 terms. We're going to the next one, which of course is x squared over 2 factorial, or just 2. Okay. And, oh, I didn't mention that it said centered at 0, so we don't have to put the x minus anything. Now it says use that to estimate e. Sometimes people get caught up on this one. They say, I can't do this one. Well, e is just e to the first power, right? That means we're just doing x equals 1, right? Which would be 1 plus 1 plus 1 squared divided by 2, or 1/2, 2.5. Is e equal to 2.5? No, but if we use the second degree Taylor polynomial, we get 2.5. We know we're off by a little bit on this one. Okay. Now it says, find the error bound of this estimate. What's the most that this can be off? Okay. So we'll calculate that. Okay, our m value. Do I need to take the derivative? No. Remember what we agreed to. If it's e to the x, we're going to say m equals 3. We got that memorized. That was up above. So we'll set this equal to 3. And since this is the second degree, we'll use 3 factorial. And then our b minus a is just 1 minus 0. Oh, that was nice of them again. All raised to the third power. Which means 3 over 3 factorial simplifies to 1/2. Okay, so the most this can be off is 1/2, which means we can absolutely guarantee you that e is going to be between 2.5 plus or minus 1/2. It's going to be between 2 and 3, which of course we know it is. Next it says, what degree Maclaurin polynomial do we need to estimate this to a degree of 5 decimals? Let's get closer than this, in other words. Okay. So, again, take a look at how this was calculated. And this is telling us that our error, maximum to 5 decimals, that is 0.1234 decimals, and then a 5. We want to make sure that we are less than that. And in our formula here, our m is 3. And then down here, this is n plus 1 factorial. And we know that this is 1 minus 0 to the n plus 1 power, which of course is just going to be 1. So now we need to figure out what the n value will be here. This is going to be just a guess and check. If it's multiple choice, you just look at option A, B, C, or D and pick one and start with it. If it's too high, go to the next one. Too low, go to the next one. Okay? So, in this case, I'm going to pull out the handy dandy calculator and see if we can figure this out. So, what's the value of n that you guys want to start with? N equals 3. So we'll put a 3 factorial in here and get my eyes up there. Math, probability, and option 4. Boom. Oops. That's 0.5. What's another value that... Oh, I should have put 4 in there. You said 3, and I messed up. Sorry about that. And let's change that to a 4 because this is 3 plus 1. It's 4. That gives us... Whoop, is that less than 0.00005? All right, so n equals 3 doesn't work. What's another one? You want to do 20? N equals 20. We'll put that in there. It would be nice if it were multiple choice and we wouldn't have to guess all over the place. Here we go with 20. Is that less than that? So 20 will definitely work, but we want the smallest number possible. So 20's too much. What's another number you want to choose?
10.
10. We'll go with 10. Woohoo! And of course I made that mistake again. If we want 10, 10 plus 1, this should be 11 in here. Made the mistake. This was 19. This one is 10 because remember it's 10 plus 1. What do we get? That is less than this one. That's our n equals 10. Okay. So remember, n equaled 20. We were at like, n equals 19. We were at 1.2 times 10 to the negative 18th. At 10, we're at 7.5 times 10 to the negative 8. What's another one you want to use? 7. Woohoo! All right, we're going to go with 7. So that means 7 plus 1. Anybody know that one? Most of you don't have your calculators. We good with 8? Is that right? Check my math. Oh, does that do it? What do you mean no? Oh man. So n equals 7 gives us 7.4404 times 10 to the negative 5th. So what do you want to think of now? Got to go the other way.
8.
Yeah. Okay. This one is a little bit too much air. This would be 0.0234 and then the 7. So yes, let's try 8. And remember, if we use 8, then 8 plus 1, our denominator has to be 9. That's a common mistake. And does that do it? 0.1234. How many zeros? 5. And then an 8. Does it do it? Does it do it? Or wait a second. Yeah. 1, 2, 3, 4, 5, 6, 7. Close. Which one you want to do? To the 9th. Okay. Second inner, which means this will be 10. 1. Is that one going to work?
Yeah.
Yes. Okay, so you can see a little bit of guess and check, made a little bit easier if it's multiple choice. Okay, but again, n equals 9 will be 3 divided by 10 factorial, which is 8.2 something times 10 to the negative 7th. And that's going to work well for us. Okay? All right. Let's take a look here. Next one, pretty similar. This time we're using the cosine, and we want it to 4 decimals. Okay? Remember what 4 decimals means. Okay? It means that this remainder must be less than 0.1234 decimals, and then the 5. Okay? Since we are using cosine, what's our m value going to be? 1. 1 over n plus 1 factorial. And since we're about 0 and x equals 1, it's a 0 minus 1 to the n plus 1 power. And that's nice because this is just going to be 1, and we don't have to worry about it. We're just going to do this again. Bless you, bless you. So, again, this is just strictly going to be a guess and check. Remember, when n equals 7, you're doing 1 over 8 factorial. When n equals 10, you're doing 1 over 11 factorial. And you're going to keep checking that and try and zoom in so that you're the closest to that. A little bit of guess and checks. Some are going to be too high, some are going to be too low until you get it. Okay? All right, let's take a look at our next one. This one says, show that the 6th degree Taylor polynomial for cosine centered at zeros gives you values which are accurate to at least 4 decimals. This one adds the little comment to it to say, hey, if I say 4 decimals, it means the same thing as to within 0.0005. Okay? So, you can see centered at 0, which means our a is 0, and it says our x's are going to be less than 1, so that means our b is 1. Okay? So, this is saying our 6th degree polynomial at 1, okay, must be less than or equal to, again, our m value is 1 since we're doing cosine, and then since this is the 6th degree, n equals 6, n plus 1 is 7. So this is 7 factorial. And then whether you do want to write it or not, the absolute value of 1 minus 0 to the 7th power, which simply is just 1 divided by 7 factorial. 1 divided by 7 factorial. We're going to check and make sure that that is less than 0.01234 zeros and then a 5. And indeed, if you do put that in your calculator, you'll get 0.1234 and then 198, which is, of course, less than 0.00005. And you have shown that that is true. Next, it says, let's find the sign of 35 within 3 decimal places. And note that you have options here to where to place the center. Okay? So, this one, we know the sine of 35, well, 35 degrees is pretty close to 30 degrees. And we know in calculus we don't deal with degrees, we deal with radians. Anybody know what radians that would be if we use 30? Pi over 6. So, to estimate 35 degrees, let's use an a value of pi over 6. Okay. Our b b value, and we could have gone up to 40 degrees or something else, but it just makes the math a little bit harder for us. And then our b value will be that 35 degrees, which actually is 7 pi over 36 in radians. Okay. So let's work this one out. So we're going to do our nth partial sum of the estimate here of 7 pi over 36. We know that our m, since this is sine, cosine, or cosine, either one of those, will have 1. And then n plus 1 factorial. And then this difference between these two. The 7 pi over 36 is our b value. Our a value is 1/6 of pi. And we're saying we want this within 3 decimals, 0.123 decimals, and then a 5. And I forgot to put the n plus 1 up there also. So this becomes 1 over n plus 1 factorial. And then the nice thing about 7 pi over 36 minus pi over 36 is this is just going to be pi over 36 to the n plus 1 power. Guess what we're going to have to do here again? Guess and check, guess and check, guess and check. Okay, so put in an n value of 2, 3, 4, 5, 6. If you want to start high at 10, go for it. And then you're going to work your way back down. I chose n equals 3. That was a little bit off. Then I chose n equals 2. And again, the nice thing about this is it's going to be multiple choice. So you're going to be limited to 4 possibilities anyway. Choose the highest one if you want, or choose one in the middle, and then work your way up or down from that. Okay. Next, it says, show that the Taylor series for sine of x converges to sine of x for all a's. What are they trying to get at here? I don't know. But let's think about this. We know that sine of x is odd. We begin with x, and then we subtract x cubed divided by x 3 factorial, and then we add x to the 5th divided by 5 factorial, x to the 7th divided by 7 factorial. We know that this is an alternating term with the n or negative 1 to the nth power. We know that the x is raised to the odd, and the denominator is an odd factorial. Okay. So let's do a quick little limit as n goes to infinity ratio test. I'm not going to worry about this n minus 1 because I'm taking the absolute value. So remember this one. Some of you mess this up. When I do n plus 1 here, this is 2 times n times the 1, and then adds 1. This is actually 2n plus 3 divided by the 2n plus 1. Then our denominator, the same thing. This will be a 2n plus 3 factorial. The numerator will just be the 2n plus 1 factorial. We're going to make sure that this is less than 1. And you can see with a little bit of algebra that the first one simplifies to x squared. And then what we're left with this factorial is just the last 2 terms in the denominator, the 2n plus 2 times the next one, the 2n plus 3, because all the 2n plus 1, the 2n minus 1, all the way down to 3, 2, 1, all get canceled out. But that didn't really matter to us. We already knew that this was going to go to what? Yes, it goes to 0. Hey, is 0 less than 1? Yes. So yes, we have shown that no matter what, this will always go to 0. Woohoo! Okay. So eventually we'll get to the point on that one, if we actually can go to infinity, that we would have 0 error on that. But of course we know we can't. Okay. Next one. Let's use the Taylor series for sine about x equals 0. And we know that it converges to sine of x for all x if the 9th degree Taylor polynomial is used to approximate the sine of 2. What is the error bound? What's our maximum error? Okay. Now, the nice thing about this one is we know that this sine curve, or f of x, remember this is odd, it's going to be x plus, minus x cubed over 3 factorial plus x to the 5th over 5 factorial plus, it is an alternating series, a negative 1 to the n, 2x to the n plus 1 over n plus 1 factorial. So we can actually say, let's use our alternating series error on this one. Which means all we have to do is the next omitted term here. So the 9th degree Taylor polynomial, think about where this fits in here. Won't we have an x to the 9th power eventually in here? This will be over 9 factorial, which means if we use that, f of x would be all of those that we have up there, and then before it would be the x to the 7th over 7 factorial. Since we stopped right here using the alternating series error, all we have to do is say our error must be less than or equal, what's the next term? What's our next term? There are 3 people that know this. Will one of them speak up? You got to do it. What's the next omitted term? Yeah, the next omitted term. So, absolutely. We're going to use x to the 11th power over 11 factorial. So, since we're estimating this at 2, we'll put in 2 for our x, and in this case, our error bound, our maximum error, will be whatever 2 to the 11th is divided by 11 factorial. And that's it. Whatever that number is. Okay, let's take a look at the next one. This one, it says we have this function, the natural log of 1 plus x, and they've given us the series that can be used to approximate that. And it says based upon the alternating series bound, bing, 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 it is alternating series with the negative 1 to the nth power. What is the least value of m such that they put all this in here. Let's try and make sense of this. Okay? So, we can see from this one that we're looking at an x equals a 0.1 here. We're x plus 1, okay, or excuse me, 1 plus x is what's here. So when it does this, it's saying that x plus 1 is 0.1 or 1/10. Okay. So that is our x value. Since it's an alternating series, we're going to use our next term, whatever that is. Okay. So Let's take a look at this. This, of course, will be the absolute value of -1 to the n plus 1. Really doesn't matter since we're doing absolute value, over n plus 1, next term, and then times x to the n plus 1. We have to make sure that this is less than 5,000. Okay. So, let's figure out, based upon this, what value are we going to have to use for this? It's going to be a little bit of a guess and check here. I do know that x is going to be 1/10, so I will put that in here. This will be 1 over n plus 1, and then plus 1/10, or 10 to the n plus 1 power. I just put in 10 in that. That has to be less than 5,000. Looks like another guess and check here. So, personally, what I did with this one is I've got ones in my numerator, so won't the denominators have to be equal to each other? So rather than always just putting 1 divided by 1 divided by, I just went ahead and used n plus 1 times 10 to the n plus 1 power has to be, and then think about this, if this is a less than, the denominators would have to be greater than 5,000. And just use that for my guess and check. You could use the fractions here and keep it as a less than, but again, substitute in n equals 4, n equals 5, n equals 3, n equals 6, and then you're just going to guess and check your way through that. Okay, next one. It says the first 4 terms of a Maclaurin series are given right here, and they converge for f to f for all values of x. Okay, they have shown the graph of the third derivative of f. This is not f. This is the third derivative of it. And bless you. And they've also did the absolute value, so whether these humps went down or which ones went above or below, we don't care, but this is the absolute value of that. Okay? It shows this for all of our x's from 0 to 0.5, and now it says, what is the smallest value of k for which the Lagrange error guarantees this? Okay? So, look at this. This is a common way that they're going to show you. This, of course, means the actual value. This one is the estimated value. So the actual minus the estimate means that this little notation here is just the maximum error or error bound. They didn't use those words at all, but they showed it to you like this. That is the maximum error, the error bound on this one. Okay? So, also, what we can see from this, it says p sub 2, so that means n equals 2, which means our n plus 1 will be 3. Also, you can see in these, it's using 1/4, so that means our b value is 1/4. Okay? So, let's go to our error bound. Remember what this looks like. This will be, in this case, the third derivative. Okay, that's the one we're asked to use, which means that if that's the derivative, we're doing this at 1/4, that's going to be third, so this must be 3 factorial. And then also, our x minus a will also be to the third power. Okay. Now, this one says, hey, we're going from 0 to 0.5, so let's use a as 0. Our b value is 1/4 minus 0, and we're saying this has to be less than k. What will that be? Okay. So, first of all, this right here we're just going to have to go over to our graph and get that value from it. Okay? Now, common mistake here is to say, ooh, isn't that 0 at 0.25? Yes, it is, but here's the stickler. This is an estimate. Okay? We want the maximum that it could be. So actually, we're using 60 for this. Because between 0 and 0.25, the largest this derivative is 0.6. Just like when we used our sine curve. The highest we were on the sine curve is positive -1. We used the maximum in that range. Okay? Not the actual value here. Okay? So this actually becomes 60, that maximum value there. We know that 3 factorial is 6. And then 4 times 4 times 4 is 64. So 1/4 cubed will be 1 over 64. Slide that in your calculator, and you'll get, what is this, 10/64, 10/64, 5/32 will be what K cannot exceed. All right. Trying to give you as many different ways the questions will be. I know it seems a little bit all over the place, but that's kind of the way the error questions are. So let's finish up with some, or no, I'll just wait. We'll do these tomorrow. So that's probably enough to get you started on these. Again, they will change the wording around a little bit, but make sure you are following that idea of 2 ways: alternating series test or the Lagrange remainder formula. Next omitted term, or just use the Taylor series. Nice job.